Have you ever noticed that really agonizing pregnant pause when you're talking to an AI assistant?
Oh, yeah. The blinking cursor.
Right. Like you're deep into this complex back and forth brainstorming session. You type a prompt, you hit send, and you just sit there. And it feels like the deeper you get into the chat, the longer that lag seems to become.
Yeah, and it's actually super fascinating because that lag, well, it reveals this kind of fundamental illusion about how these systems actually operate.
An illusion.
Yeah, I mean, as users, we perceive this continuous flowing conversation, right?
Hmm.
But under the hood, the reality is remarkably different. That lag you're seeing is the outward symptom of a massive computational bottleneck.
Wow. Okay, well, today we are taking a deep dive into an incredibly detailed source that explains exactly what this bottleneck is and how engineers are actually trying to fix it.
Right.
We're looking at this really cool narrative-style blog post. It's called The Secret Life of Azure the Memory Architect. It's by Aaron Rose from tech-reader.blog.
Specifically, episode 35 of his series, I think.
Yes, exactly, episode 35. And the whole piece is dedicated to unpacking how developers are basically eliminating what they call the rereading tax.
Which is a great term.
It really is. They're doing this using intelligent context management to give AI systems a sort of short-term memory so they can actually converse fluently without just completely wasting computing power.
And I love how Aaron Rose frames this whole technical exploration. He does it as a story.
Yeah, the story format makes it so much easier to digest.
Totally. So we follow these two characters. There's Margaret, who's this senior software engineer, and Timothy, her junior colleague.
Right.
And they work in this grand Victorian library in London.
Right, which is just such a vibe.
It is. And the setting itself is kind of a metaphor for the system architecture, you know? It's a place where craftsmanship and meticulous organization are just absolutely paramount.
Well, when I first read about this whole lag issue, the baseline problem struck me as very human.
How so?
I mean, interacting with an unoptimized AI, it's essentially like having a coffee date with a friend who has like severe short-term memory loss.
Oh, that's a really good way to put it.
Right. You
Yeah.
sit down, you introduce yourself, and you have to give them your entire life story up to that exact moment. Then you ask a question, and they give this highly intelligent answer.
But then 3 minutes later.
Exactly. 3 minutes later, you ask just a really simple follow-up question, and they just stare blankly at you.
Because they've completely forgotten you.
Yes, you literally have to recount your entire life story and re-explain the conversation you just had just to give them the context for that one tiny follow-up.
And mathematically speaking, that is the defining characteristic of a stateless system.
A stateless system. Okay, break that down for us.
Basically, a raw, unoptimized, large language model retains absolutely zero memory of the previous interaction. None. It operates entirely in a vacuum.
So it's literally starting from scratch every time.
Exactly. To generate the next word in a chat, it has to ingest the entire chat history from the very beginning, process all of it, and only then can it formulate a reply.
Which brings us back to Timothy in the story. We find him pacing in this beautiful library, dealing with this exact issue. He has his smart router, shunting traffic. He's got his quantized specialists answering things super fast. But his system is just dragging on this one metric.
Right. First token latency.
Yeah. What exactly does that measure?
So first token latency is simply the time it takes for the AI to output its very first character after you hit send. It is, well, it's pretty much the defining metric for AI fluency.
Because if it's high, the machine feels sluggish.
Exactly. High latency makes it feel like a clunky machine. Low latency makes it feel like an actual conversational partner.
Okay, so Timothy realizes his system is smart, but just wildly repetitive. And this is where Margaret steps in, right? She picks up this deep purple marker, draws a bookmark inside this thick technical manual, and she introduces the concept of the rereading tax.
Yeah, she realizes Timothy is treating every turn in the conversation as an isolated event.
It's like forcing a librarian to reread chapters 1 through 5 of a book every single time you ask a question about chapter 6.
That's essentially what it's doing. And she draws this really hard line between stateless prompts and what she calls active memory management, or contextual persistence.
Contextual persistent.
Right. Active memory management is basically the architectural attempt to give the system short-term memory so it can completely bypass that tax.
Now, I have to say, when I was reading about this rereading tax concept, I was really trying to reconcile it with modern hardware.
I mean, it sounds a little counterintuitive at first.
It really does, because, look, we are dealing with computers that can search vast databases in a fraction of a second, right? Processing a few paragraphs or even a few pages of a text chat seems incredibly trivial.
Yeah, you think so.
Like, rereading a simple text file shouldn't cause a noticeable lag, right? I mean, why does it matter?
Well, the catch is that if the computer were simply, reading text left to right to find a keyword, you're right, it would be absolutely instantaneous. But neural networks do not read.
They don't read.
No, they compute attention.
Okay, what does that mean in practice?
When a model processes a prompt, it's calculating the mathematical relationship between every single word and every other word in the sequence to determine the context.
Oh, wow. So, like, if the word bank appears, it needs to look at the rest of the sentence to calculate if we are talking about a riverbank or a financial institution.
Yes, and it doesn't just do that sequentially. It does this for every word simultaneously. It's basically building this massive, complex web of geometric calculations.
Okay, that sounds heavy.
It is incredibly heavy. The complexity scales quadratically. So if your conversation doubles in length, the mathematical lifting doesn't just double, it quadruples.
Wait, it quadrupled?
Yeah. So the rereading tax is not just the act of scanning a text file. It is the staggering computational overhead of recalculating that entire geometric web of attention for the entire history of the conversation.
From scratch.
From scratch, for every single new word it generates.
Okay, that reframes the problem entirely. It's not just reading. It is recalculating the entire universe of the conversation every single time I hit send.
Exactly. Which brings us to the very first optimization Margaret teaches Timothy to try and stop this massive waste of resources.
Right, because if the math is exploding because the system is recalculating everything, the obvious starting point is to just lock down the elements of the prompt that literally never change.
Which is where she goes to the whiteboard.
Yeah, Margaret draws this solid block at the start of a text stream on her whiteboard, and she calls this prefix caching, or the static cache.
So to understand this, you have to know that every AI prompt usually begins with a hidden block of text called system instructions.
This is the stuff we as users never see, right?
Exactly.
Yeah.
Before your actual message even starts, the system is fed all these foundational rules. Things like, you are a helpful assistant. Here are your safety guidelines. Here is your persona.
And those rules are identical every single time you start a chat.
Every single time. So instead of forcing the system to perform that massive web of geometric calculations for the exact same instructions on every turn, it does something smarter.
It calculates it once.
Right. It calculates the attention web for those rules once, gets the mathematical result, and then locks it into a high bandwidth cache.
And Aaron Rose makes a great point here about scale, because the real power of prefix caching becomes apparent when you scale it up, right?
Massive.
So, like, if 10,000 different users log in and start a chat with the exact same system instructions, the model does not recalculate that foundation 10,000 times.
Right, that would be a nightmare.
All 10,000 sessions just share that one single cached computation.
Which is brilliant.
I was trying to think of an analogy for this, and it made me think of working in a busy restaurant kitchen.
Okay, let's hear it.
So imagine you hire a new chef, and there's this dense 50-page health and safety manual they must follow. In a stateless kitchen, every time a waiter brings in a ticket for, say, a burger, the chef pulls out the 50-page manual, reads it cover to cover, internalizes the safety rules, and only then looks at the ticket to start cooking.
I mean, that burger would take hours.
Right, you'd never get your food. So prefix caching is basically the chef memorizing the manual once before their shift even starts. The rules are locked in. When the ticket comes in, they recall the rules instantly and just start cooking.
I like that. The foundational rules are static, so the memory of them is static. The model bypasses the computational read and performs just a millisecond recall.
But Timothy is pretty sharp, and he immediately spots the limitation here.
Because prefix caching only solves half the problem.
Exactly. The system instructions are static, sure, but the actual conversation between you and the AI is highly dynamic. It changes and expands with every single sentence you type.
Right, so we need a way to track a constantly evolving chat without triggering that rereading tax all over again.
And Margaret addresses this on the whiteboard, right? She draws a series of interconnected nodes and introduces the dynamic stream.
Powered by KV caching.
KV caching, key value caching. So instead of storing the raw text of the conversation, the system is storing the intermediate mathematical states of the generated words.
Which Margaret beautifully refers to as the mathematical fingerprints of the conversation.
Mathematical fingerprints. I love that phrasing. But what exactly is a key and a value in this context?
So As the AI generates a word, it's computing these really complex beta points. It stores the key, which essentially represents a word's specific position on context within the sentence.
Okay.
And then it stores the value, which represents that word's mathematical contribution to predicting the next word in the sequence.
Yeah.
So it's saving the mathematical weight and context of a word at a specific moment in time.
I was really trying to visualize how key value caching actually speeds up the generation process, and I kept thinking about calculating the trajectory of a billiard ball bouncing around a table in a physics simulation.
Oh, that's interesting. Walk me through that.
Okay, so in a stateless system, to figure out where the ball will be at, let's say, second number 10, the physics engine literally has to start at second 0. It has to calculate the initial strike, then the first bounce, then the second bounce. It's basically replaying the entire timeline from the start just to calculate the very next frame.
And the computational cost of resimulating the entire past just to predict one step into the future is enormous.
Exactly. So KV caching steps in by basically saving the active state. It saves the exact current coordinates of the billiard ball, that's your key,
Right.
and it saves the ball's current momentum and direction, that's your value.
I see where you're going with this.
So when it's time to calculate the next millisecond, you don't sprint all the way back to replay the entire simulation from the beginning. You just take the key and the value, plug those two numbers into the equation, and generate the next frame. You're just carrying the momentum forward.
That is a perfect way to visualize it. When it's time to generate the next word in a chat, the agent doesn't look back at the raw text and recompute that huge attention web.
It just looks at the breadcrumbs.
Exactly. It accesses those key and value fingerprints. It follows its own mental map, which turns this massive recalculation into a simple memory retrieval.
But my concern here, and honestly Timothy brings this exact thing up in the library as well, is the physical limitation of the hardware itself.
Yeah, the storage problem.
Right. If the AI is constantly generating and storing these really dense mathematical fingerprints for every single word in a massive, say, hour-long research session, the computer's memory is going to fill up incredibly fast.
Oh, it absolutely will. Giving a system memory inherently introduces a storage problem. Because these key value fingerprints, they live in the memory of the GPU, which is incredibly expensive and highly, highly constrained.
So how do they keep it from crashing? Margaret draws this grid of small, flexible memory blocks on the whiteboard to illustrate this, right? She calls it paged memory management, or the paging architect.
Yes, she explains that they break the conversation down to fixed-size pages. It acts a lot like a computer's RAM.
But why fixed-size pages? Why not just give the user a big chunk of memory?
Well, if you assign memory in giant contiguous blocks, say, reserving a massive chunk of GPU memory for a user just in case they have a long conversation, you create what's called memory fragmentation.
Ah, okay.
Because if the user only types a few sentences, the rest of that massive block just sits there entirely empty. The GPU gets clogged up with all this empty reserve space, and eventually the system chokes because it can't accept any new users.
It's just wasting expensive real estate.
Exactly. So by using small, fixed-size pages, the system only allocates the specific chunks of memory the AI actually needs at that exact moment.
But wait, if we aren't reserving one giant continuous block of memory, then we must be chopping the conversation up, right?
Right.
And scattering it across whatever small empty spaces are available on the physical chip.
Correct.
So how does the system read a continuous thought if the data is literally fragmented across completely random physical locations on the hardware?
So it uses a technique that's actually heavily inspired by traditional operating systems, virtual memory mapping and lookup tables.
Lookup tables?
Yeah. So from the perspective of the AI model, it actually thinks it has one contiguous, unbroken block of memory to work with. It asks for the sequence of the conversation in perfect order.
But behind the scenes, that isn't the physical reality at all.
Not even close. The paging architect maintains a lookup table. Think of it as a master index.
Like a card catalog in our Victorian library.
Exactly. When the AI model asks to retrieve, say, page 5 of the conversation, the lookup table intercepts the request and says, oh, page 5 of this chat is actually stored way over in physical block 912.
Oh, I get it. And then when it asks for page 6,
The index points it over to physical block 14.
and the system only allocates a new page when the previous one is completely full of those mathematical fingerprints.
Right, which completely solves the fragmentation problem. The hardware stores the data wherever it naturally fits, maximizing every single inch of space, while the lookup table ensures the AI model still experiences a perfectly ordered, continuous stream of memory.
Margaret describes it as managing the GPU's memory like a master librarian handling a restricted archive.
Which perfectly brings the story full circle.
It really does.
Mhm.
So let's recap where we were. We have prefix caching, locking in the permanent rules so they are never recalculated.
Right.
We have KV caching, tracking the dynamic mathematical momentum of the actual conversation.
Yep.
And we have paged attention, utilizing lookup tables to ensure those fingerprints are stored efficiently without wasting any hardware space.
And when you combine all three of those, that constructs the memory architect. The AI is officially cured of its short-term memory loss.
It's amazing. And Aaron Rose actually closes his story by bringing us right back to the terminal. Timothy is sitting there, watching a user engage in a really complex 20-turn research session.
Now, in a stateless system, the rereading tax would have slowed the output to an absolute crawl by turn 20.
Because the geometric math would have just overwhelmed the processor.
Exactly. It would take forever to get a response.
But instead, Timothy watches the responses come back instantaneously. The terminal flashes with this purple cache hit light, and it's just flickering constantly as the system pulls from the static prefix and the dynamic key value tables instead of recalculating everything from scratch.
The agent isn't just answering anymore, it is flowing. Because it actually remembers exactly where it is in the context of the interaction.
Margaret caps her purple marker with this final concluding thought, which I really loved. She says, in the race for efficiency, the winner isn't the one who reads the fastest. It's the one who never has to read the same thing twice.
It highlights such a profound shift in computing philosophy, honestly.
Yeah.
The real frontier of optimization isn't just about raw processor speed anymore. It's about having the architectural intelligence to perfectly index what you've already computed.
So for you listening, the next time you have a seamless hour-long chat with an AI assistant and there is zero lag, you'll know the machine isn't just miraculously reading faster.
No, the memory architect is behind the scenes, mapping lookup tables and tracking the mathematical momentum of your words.
They have essentially engineered a way for the machine to hold the thought.
Which is incredible.
It is. But as we wrap up this deep dive into the source material, there is a lingering implication about this technology that I think is really worth exploring.
Okay, let's hear it.
Currently, this short-term memory we've been talking about, it exists only while your browser window is open, right? The system stores the mathematical fingerprints of your conversation, but when you close the chat, the pages are cleared.
Yeah, the lookup tables are completely wiped to make room for the next user.
Yeah.
The memory is temporary by design.
But consider what happens when this highly optimized memory architecture inevitably scales. If the absolute pinnacle of computing efficiency is to perfectly store the mathematical fingerprints of a conversation so the AI never has to recalculate it,
Yeah.
what happens when storage becomes so vast and caching becomes so advanced that the system literally never flushes the cache?
Oh, wow. You're talking about a continuous state that stretches indefinitely.
Exactly. Will there be a day when an AI never rereads a single interaction from your entire lifetime?
That is wild to think about.
Imagine your lifelong relationship with a digital assistant. Every brainstorm, every late-night question, every single project you've ever worked on together. It isn't saved as a series of disconnected text files. It is stored as one massive, instantly accessible, never-forgotten mathematical fingerprint.
So it literally carries the momentum of your entire history together.
Yes. You log in 20 years from now, and the context of your entire life is just a millisecond cache hit away. What kind of relationship do we build with an entity that perfectly retains the mathematical momentum of our entire minds?
That's pretty profound.
That is something for you to ponder the very next time you see that blinking cursor.